American cheese looks simple, but the process behind it is built on precise control from the very beginning. What makes a difference starts with a decision that goes against traditional cheese making. Instead of beginning with milk, it begins with cheese that already exists. That alone changes everything. Traditional cheese develops from raw milk through biological processes. Bacteria converts lactose into acid. Enzymes like rennet causes proteins to coagulate. Curds form, moisture is removed, and the structure slowly develops. Texture and flavor evolves over time, influenced by aging, temperature, and microbial activity. The outcome is not fully predictable because small variations can change the final product. American cheese avoids the variability by starting with finished cheese. The base materials are usually cheddar, Colby, or similar mild cheeses. These are selected not just for flavor, but for composition. Each cheese contributes specific ratios of fat, protein, moisture, and acidity. Cheddar provides structure and a relatively firm protein network. It also contributes a slightly acidic profile that affects how proteins behave during heating. Colby contains more moisture and a softer structure, which improves meltality and reduces rigidity. Other cheeses may be included in smaller amounts to fine-tune these properties. The age of the cheese is also important. Younger cheese contains more moisture and has a less developed protein network, making it easier to melt and process. Older cheese has stronger flavor but a tighter protein structure, which can resist melting and produce a grainy texture if not modified. By combining cheeses of different types and ages, manufacturers define the starting balance of structure and melt behavior. Only the cheeses are selected. They are prepared for processing. Outer rinds are removed because they introduce inconsistencies and can interfere with uniform melting. The cheese is then reduced in size by grinding, shredding, or chopping. This step is essential for achieving uniformity. Natural cheese does not melt evenly when left in large pieces. Heat penetrates unevenly, causing some areas to soften while others remain firm. This creates instability in the system and can lead to separation of fat and protein. By reducing the cheese into small uniform particles, heat can be applied evenly, and later mixing becomes more effective. At this point, the material is still natural cheese, but it has been physically modified to allow controlled processing. The transformation begins when additional ingredients are introduced. The shredded cheese is transferred into a mixing system where components are added to adjust composition and functionality. Water is one of the most important additions. It controls moisture content, which directly influences texture and melt behavior. Higher moisture leads to softer, more spreadable products, while lower moisture produces firmer structures suitable for slicing. Milk or cream may be added to standardize fat content. This ensures consistency between batches. Since natural cheese can vary slightly in composition, milk proteins such as caseinates or whey proteins are sometimes included to strengthen the protein network and improve stability. In certain formulations, small amounts of stabilizers or starches are added to influence viscosity and water binding. These help maintain a uniform texture and prevent separation under different conditions. Coloring may also be introduced to achieve the desired appearance, which can range from white to pale yellow or orange. However, the most critical addition is emulsifying salts. These salts define the behavior of the final product. Common examples include sodium citrate and sodium phosphate. Their role is to modify how proteins and fat interact within the cheese system. Emulsifying salts change this behavior at a chemical level. They bind to calcium ions within the casein structure and disrupt the original protein network. This reduces the tendency of proteins to clump together. At the same time, they increase the ability of proteins to interact with water, improving hydration. Most importantly, they allow fat to remain dispersed throughout the system instead of separating. Fat is broken into small droplets and stabilized within the mixture. The result is a stable emulsion where fat, water, and protein remain evenly distributed. This is the key mechanism that allows American cheese to melt smoothly without separating. Once all components are added, the mixture is blended into a uniform mass. The proportions of fat, moisture, and protein are carefully controlled at this stage. For example, spreadable processed cheese may contain significantly higher moisture, often between 20 and 40% added water. Sliceable or block forms contain less moisture, typically between 2 and 25%. The amount of emulsifying salts is also tightly controlled. Too little will not stabilize the system properly. Too much can weaken the structure and produce an overly soft or pasty texture. At this stage, The mixture resembles a thick paste composed of finely dispersed cheese particles and added ingredients. It is uniform in composition, but it is not yet stable. Stability is achieved through heat. The mixture is transferred into processing equipment, such as a batch cooker or a continuous cooker. Heat is applied, typically raising the temperature above 70 degrees Celsius. This stage serves several critical functions at once. First, it melts the cheese completely, allowing all components to merge into a continuous phase. Second, it activates the emulsifying salts, enabling them to fully interact with the protein network. Third, it pasteurizes the product, reducing microbial activity and extending shelf life. During heating, the mixture is continuously mixed to ensure uniform temperature distribution. This prevents localized overheating and ensures that all parts of the mixture undergo the same transformation. The rate of heating and intensity of mixing must be carefully controlled. Insufficient heating leads to incomplete emulsification, while excessive heating can degrade proteins and negatively affect texture. As heating continues, the system undergoes a structural transformation. The original cheese matrix breaks down, proteins are redistributed and modified. Fat is dispersed into small droplets throughout the mixture. Water becomes integrated into the protein network. The system transitions from a collection of solid cheese particles into a homogeneous, viscous fluid. At this point, it no longer behaves like natural cheese. It has become a controlled emulsion with predictable properties. Once the mixture has reached this fully melted and emulsified state, it is uniform, stable, and continuous. But the process is not finished. At this point, the system still needs refinement and structural setting to achieve the final properties associated with American cheese. Even though the mixture appears smooth, small variations can still exist at a microscopic level. These variations can affect texture, mouthfeel, and how the product melts during use. To eliminate these inconsistencies, the mixture often undergoes additional mechanical treatment. High shear mixing or homogenization is applied to further refine the structure. This process reduces the size of fat droplets and distributes them more evenly throughout the system. Smaller droplets create a smoother texture and improve stability by reducing the likelihood of separation. At the same time, proteins and water are redistributed more uniformly, ensuring that the internal composition is consistent throughout the entire batch. After refinement, the mixture remains hot and fluid, but it now has a highly uniform internal structure. The next step is cooling, which determines how that structure is fixed into place. Cooling is not a passive stage. It is a controlled process that defines the final texture and physical behavior of the cheese. As the temperature decreases, the protein network begins to reorganize and stabilize. Fat droplets become immobilized within this network, and water remains bound to the proteins. The rate of cooling has a direct impact on the final product. The final structure must be stable when cold, but capable of softening evenly when heated. Once the structure has begun to set, but the mixture is still partially fluid, it is directed into shaping systems. The method used depends on the final form of the product. For block cheese, the mixture is poured into molds. These molds define the shape and size of the final product. The cheese is then allowed to cool gradually until it becomes fully solid. The result is a dense, uniform block that can be sliced or used in bulk applications. For slice production, the process is more controlled. The mixture is spread into thin layers using specialized equipment. Thickness is carefully regulated because it directly affects melting behavior. If the slices are too thick, they may not melt evenly. If they're too thin, they may lack structural integrity. Once the layers reach the appropriate consistency, they are cooled further until they can be cut into uniform slices. Each slice is typically separated by a thin film or wrapper. This prevents sticking and ensures that slices can be handled individually without tearing or deforming. For spreadable products, the mixture is cooled more quickly and packaged before it fully solidifies. This preserves a softer texture that can be easily spread after refrigeration temperatures. At this stage, the product has taken on its final physical form, but it still requires packaging to maintain stability. Packaging serves several important functions. It protects the cheese from contamination, prevents moisture loss, and limits exposure to oxygen. These factors help preserve the internal structure that was established during processing. Once packaged, the product is ready for distribution and use. The defining feature of American cheese becomes most apparent during reheating. When heat is applied, the structure formed during processing responds in a controlled manner. The protein network softens gradually without collapsing. Fat remains evenly dispersed and does not separate as free oil. Water stays bound within the system, maintaining a smooth consistency. As a result, the cheese melts into a uniform, continuous layer. The smooth melt is not accidental. It is the direct result of the emulsifying salts, the balanced composition, and the structural changes created during heating and mixing. The entire process is designed to produce a material with predictable functional properties.